few weeks back, there was a 10.7 billion parameter LLM whose performance was on the top in the Open LLM leaderboard. So this was a model called as SOLAR 10.7 billion instruct from a startup called Upstage AI, startup or labs called Upstage AI. So I was curious, like, how come a 10.7 billion parameter could top this Open LLM leaderboard, where you had all these other 70 billion parameter models, your 30 billion parameter models, okay? But this 10.7 billion parameter model could top this leaderboard. The first thing that went into my mind was probably there is data contamination in the training data from these benchmarks. But then later I found out that they did something called as depth upscaling. So they changed the architecture a bit. So they continued pre-training. So what they did over here was that they integrated Mixtral 7B weights into the upscale layers and finally continued pre-training for the entire model. I'll explain what is this depth upscaling in another few seconds. So this model outperforms models with 30 billion parameters, even surpassing the recent Mixtral 8/7 billion model mixture of experts. Right, so this is what they did. And they did instruction fine-tuning using a combination of supervised fine-tuning and direct preference optimization. I've explained direct preference optimization in a previous video when I was talking about Zephyr Beta, right? So let's look into what is this depth upscaling technique. Okay, so here they talk about depth upscaling. There is this description figure which describes it. So the idea over here is that they initialize the base model is a 32 layer Llama 2 architecture, which they initialized with pre-trained weights from Mixtral 7B. Okay, which is one of the top performers compatible with the Llama 2 architecture. So that is your base LLM. What they then do is that then they make a copy of this base LLM. So here you have a copy of this particular base LLM, which is a Llama 2 but initialized with Mixtral weights. So you have a copy of that. Okay. Then what they do is that from one of these models over here, they drop the top 8 layers. From the other model, other copy, they drop the bottom 8 layers. Okay. So you get 24 layers each. Then they merge these 24 layers to get a 48 layers new model. Okay, and then they continue pre-training on that to get your final model. This is the idea of depth upscaling. That is what they've explained over here. Okay, this is what they talk about depth upscaling. Alright, so what they are doing is that with this, you have two 7 billion parameter models, but when you combine them, you get close to 10.8 billion parameters. And this is the new scaled model. That is the idea which they have explained over here. The base model with n layers is duplicated for subsequent modification. They remove the final m layers from the original model and initial m layers from its duplicate, thus forming two distinct models with n minus m layers. The two models are concatenated to form a scaled model with 2 into n minus m layers. So note that n is equal to 32 from our base model. We said the scale is 48. That is the requirement. So based on that, you get this particular 48 layers model. That is the idea over here. And then they do continued pre-training on their training data. So that is what is explained over here. What they are saying is that you could also do just repeat layers once more from n to 2n layers. You can make a copy of the same model, right? But then they are saying that the layer distance or the difference in the layer indices in the base model is only one bigger than one, whereas layers n and n plus 1 are connected. This results in maximum layer distance at the seam, which may be too significant of a discrepancy for continued pre-training to quickly resolve. So instead, what they are doing is that they are sacrificing 2m middle layers, which helps it to, improve pre-training. That is what they are saying over here. Okay. So based on this particular architecture, they have actually trained on these various data sets like Alpaca GPT-4, OpenOrca, SynthMath Instruct dataset. Okay, SynthMath Instruct is a dataset where they have rephrased math questions from say math data from this GSM 8K dataset. Right, so they have trained on these datasets, and this particular model shows better performance on all benchmarks when compared to even Mixtral 8.7B Instruct model, which has 47 billion parameters. It does even better than Quen 72 billion parameters, right? That's what they are saying. So they have two models over here, the base model and the instruction tuned model. Okay. So the instruction tuned model kind of outperforms all these other models over here. So that is the idea. Some other interesting things from this idea was that they also tried combining, say, models which are only fine-tuned on one data set. So for example, they combined two models which were like SFT v1, which was only on the Alpaca GPT-4 dataset. Another one used another dataset called OpenOrca, and SFT3 we use as Synth, and then Math Instruct datasets along with dataset used in was this particular SFT v4. So what they found out was that when you just average the weights of two models and create a new model, okay, for example SFT v3 and SFT v4 over here, the newer model had very good performance. This was by simple averaging the model weights. Now what does this lead us into? So you can actually combine multiple LLMs of the same architecture which have been trained on different tasks by just simple averaging of weights, and that can give you better performance. That is what they have told over here. Right, the merged model retains high performance scores. That is what they are saying over here. This is an interesting insight for me. Okay, whereby they say that if you can combine two models which have been trained on different tasks, have the same architecture, you are just averaging the weights. This new model can give you better performance across both. So that is an interesting statement. Okay, that's again, it needs to be verified, but from whatever the results which are being, what they are saying is that merging models that specialize in different tasks is a promising way to obtain a model that performs well generally. Okay, that's the idea over here. So if you have two specific models which are excellent in different tasks, combining them will give you an overall general model. That is the this upstage the solar architecture, the solar series of models. Okay, and how a small model is able to perform on the benchmarks better than other models as well. Because for example, they also talk about data contamination tests, and they say that their model with result less than 0.1% being well indicates that model is free from contamination. That is their claim. Because they are doing so well on benchmarks, the question obviously comes whether there was data contamination. So they say it's not present over here. Okay, and this model can be used as other models in transformers, using this code. So you can go and try it out as well. The only catch over here I found out was that this model is licensed as, let me see, there is a license as CC by NC 4.0. The base model is Apache 2.0. The instruct tuned version is this. So this actually cannot be used for commercial purposes because some non-commercial datasets were used for instruction fine tuning. But the base model, I believe, can be used for commercial purposes. So this was a short video on model merging and the Solar series of LLMs. I like this idea of model merging with which you could create more powerful LLMs. The techniques which have been described in this paper seems to be simple, but yeah, the results are quite excellent. I hope this video is useful to you. If you like the video, please like, share, subscribe to the channel. I'll be putting all the links in the description of the video. You can check it out. See you in another video.